So if that thing were lying on the ground over there, what would it look like to me?
Opposite of a rainbow.
It would look like a mirror if it was made out of glass like this. Because what I would see when looking at it is I would see reflected light from the far wall. So looked at from a grazing distance, it would look like a mirror. Now, that's maybe not so amazing. Watch this. This is glass, right? Oh, I can see the lights on the ceiling. I can. Because you've seen light reflecting off the glass. So maybe that doesn't seem so amazing that these glasses would make light reflect. But what does seem amazing is the phenomenon from the last part of the problem. Part C. While driving on an asphalt road in the heat of the summer, you notice that the road ahead of you appears to be wet. Why does it appear to be wet? What's the characteristic that makes you decide that something is wet? It's shiny and it's reflecting the sky. So you see a reflection of the sky on an otherwise, apparently just asphalt road. However, as you approach the wet area, it seems to move away from you, always remaining well ahead of your car. Explain. Yeah.
All the whole floor is wet, but your headlights or whatever you use to reflect.
I'm going to disagree. Not your headlights. You're not using headlights at all. It's the middle of the day. Yeah.
The index of refraction for the air when it's really hot, close to the hot asphalt.
Yes. So the air where it's really close to the hot asphalt has what? A higher or a lower index of refraction? Lower. So the lowest index of refraction is at the bottom, and the highest index of refraction is at the top. Look at these layers. 1.1, 1.3, 1.2, 1.1, and we managed to make a reflector. If this original ray had gone in like this, would it reflect? No, because we wouldn't be beyond the critical angle here. But if it was even more tilted, then what would it do? It would reflect. So, you will reflect the sun's light off of an asphalt surface as long as the sun's light is coming and grazing to the surface, which means that you, a certain height off the surface, you got to be this far away. As you head over to here, the sun's light won't reflect off of there to you, but it will reflect over here. So as you drive along, from here, right there, you see a reflection of the sunlight that looks like the road is wet. And as you drive along, the wet patch runs in front of you. Now what makes it even more appear like water is that these temperature changes, causing index of refraction changes due to density changes, they're not perfectly uniform and smooth. There's a little bit of breeze blowing and they're fluttering. And so this surface looks like there are waves on the water. And so that's why it looks even more water, because you see a reflection with ripples in it. And the thing you're most used to having reflection with ripples is surface of the water. So that's why it looks wet. And this is known as a mirage. So, oh, it's out in the desert. Look, there's water. But it's going away from me. Is it water? No, the mirage does not involve palm trees, camels, tents. It just looks like the sand is wet in front of you and you think that it's an oasis. There are no people there waving, come on, we have water. It just appears to be wetness. But in the cartoons, people have heard of mirages. So Bugs Bunny in the desert sees the camels and the palm trees. So, okay, any question on this problem? So this problem also brings in the total internal reflection.
Lenses now.
Aha! Lenses!
It's too dry for me. It's not interesting. But you wear them.
Okay, how many of you, and I know some of you did because I saw you, how many of you went down to that big reflector in the basement of math to play around with it? Good. It was cool, wasn't it?
You got it.
You reach out and that image is in midair, and then you push your hand behind it and it's nowhere near the surface. Okay? It's fascinating. So that's why images can be cool. I once designed something. It doesn't work quite as well as I thought, but the idea was we can make lenses just out of a curved surface, right?
Yeah.
If we make lenses just out of a curved surface, then you can imagine an aquarium. You know these aquariums where you walk by next to the big wall? Where the big wall isn't flat, but it's curved.
You monster.
And so what you can do is you can make a real image. Okay? And so the design was, okay, I'm standing here. And the wall of the aquarium is over there, and I'm watching these fish go by. And then if one of them comes fairly close to the glass, it's right on top of me! It's been put in a Shark Tank. Okay? So, it was a great idea, except you tell me what would be the flaw in that idea.
The shark will crash through.
No, not panic, not the shark
The large
crashing.
radius of curvature wouldn't be, you'd have to be...
It would have to be a fairly noticeable radius of curvature, so you might know something was up, but there's a worse problem. If I just made one focusing lens out of the boundary.
It would only work at that one point.
Yeah, the shark would be swimming among us, but there'd be something odd with the way the shark was swimming. He'd be upside down.
Yeah.
Right? If you have one focusing lens and you make the image from one focusing lens,
You're right.
the magnification is negative. He'd be upside down because the object distance is positive, the image distance is positive, the magnification would be negative. So it would be really cool. It would be this upside down shark right there. So, you know, it needs work. But well, I can tell you, if you've had something like that in an aquarium, it is my belief that the kids would just stay there for the entire aquarium visit, right? They'd be there, and then the fish would come towards them, and they run back, and then they run forward, and then try to touch it.
But they won't be able
It'd be great. It would be the #1 attraction at any aquarium anywhere.
But they won't be able to
But they would notice that the fish are upside down. So, yeah. The question. Oh, could you give them glasses as they went in that flipped the image? Yes.
It would flip everything.
Yeah.
Yes, it would flip everything. It would be very hard to walk.
I'm not excited.
You know, as you're going along, you look out. Oh, I see my hands at the edge of my vision. They're above my head. Okay? And oh look, there's my foot way up there. Whoa! I got to put my foot on the ceiling. It would not be nice. But I talked about that experiment they did in the Navy, right?
Yeah.
They gave everybody these glasses to flip upside down. It's crazy. Well, you know, if the kids could stay for 3 days, and then you send them home to their parents. Clean up your room. I can't get it.
But if they wear the glasses, won't the shark still be flipped upside down? If they keep wearing the glasses, won't the shark be still upside down? Doesn't mean they have to take it off when being a shark?
Oh. Right. So what would happen is you would put on the glasses and the shark would be right side up, but the world would be wrong. Okay. And then after a little while, okay, great. So now the shark is upside down again, and the world is right. Oh no, the world is wrong. So yes, you get 2 opportunities to watch the shark. So you watch the shark for 3 days like this. Watch the shark for 3 days like this. Then you go home. So the only option is the permission slips for a 6-day field trip.
Oh, well, I mean, the current shark's not like it. They get a lot of vision.
Who did that?
Okay, who brought beer in here? Yeah, whoever brought beer in here, see me after class. So, now, the key to a problem like this is...
That makes it understanding too.
Really?
Labeling carefully, incoming and outgoing side. For lenses, what does the light do? Goes through. So one is the incoming, one is the outgoing side. Okay, so in this system, for the first lens, in is and out is. For the second lens,
They're both left.
in on the left and out on the right. They're both lenses, so the light will go through both of them. And at the end, you're going to stand somewhere over here. That's the international symbol for an eyeball, so that's an observer. Whatever. So you're going to look from over there, and whatever is the location of the final image from this guy, that is what you are going to see. Okay? Now, the way you do an analysis like this is you deal with the lenses one at a time. You take the first lens and pretend the second one isn't there. Let it form an image. The image that you get from the first lens is the object for the second lens, and then you analyze the second lens as though the first one wasn't there. Okay? And that will do the whole thing. So we got ourselves 20 centimeters, no, 30 centimeters here. We've got 20 centimeters between them. We've got absolute value of focal length. The first one is 15, and the second one is 20. Why do I give absolute values of focal length when I hate absolute values so much? I want you guys to prove to me that you can recognize which one of these has a positive focal length and which one of these has a negative focal length. Which one of these two items has a positive focal length? Yeah, the first one on the left, because focal lengths are positive when? Converging elements. And the second one has a negative focal length because? Diverging length. Okay. And that's it. That's all I need. So, the equation for lenses is 1 over distance object plus 1 over distance image is 1 over focal length. Okay?
Might as well test that.
And the main thing to keep straight in every lens calculation is the sign of every term. So, the object distance is positive when the object is on the incoming side. The object distance is negative when the object is not on the incoming side. Okay? Image distance is positive when the image is on the outgoing side, and the image distance is negative when the image is not on the outgoing side. Okay? The reason we say it in that strange way, which sounds like weird English, is that for a mirror, the incoming and the outgoing side are the same side. Whereas for a lens, the incoming and the outgoing side are opposite sides because light goes through the lens, but it bounces off the mirror. And by saying it the way we're saying it, we have one rule independent of whether we're using a lens or a mirror. Is or is not on incoming side for the object, is or is not on outgoing side for the lens. Outgoing side for the image. Okay? So far so good? Alright. What do we know for the first lens?
30 centimeters. Yeah.
Yes, we know the object distance, DO, is what?
0.03
30 plus or minus?
plus.
Plus. Because the object is on the incoming side of this lens. Now, there's one other thing. Object and image distances are measured from where?
Lens.
From the lens or mirror. Okay? So, that's why this is 30. If this lens was not there, this object would be at 50 for the second lens. Okay? So, it's always from the lens. Alright, and the focal length, so that's DO1. What is F1?
15 centimeters.
Positive or negative, and why?
Positive.
Positive because converging.